Good morning, everyone, and welcome to the fifth webinar of the IPCEI ME community. We will wait a few more seconds, let's say 1 minute, for everyone to join in this meeting and before we go ahead with the webinar. But we're glad that you're already so many to join us in time. So I see we're already more than 70 participants. We know that this number will still raise, but let's start the webinar. To not lose any time and to give you enough time at the end of the webinar to ask your questions as well. So my name is Mirelle Tever. I'm program leader at ABGI France, and we are supporting the Transform group of the IPCEI ME community in organization of events like this webinar. And today we're very pleased to welcome you to the fifth webinar already of the IPCEI ME program, which is about bridging photonics and microelectronics with the insights from 3 IPCEI ME experts. So I'm very happy to welcome today Professor Andreas Waag, who is specialist in nitride semiconductors and photonic integration at the Technische Universität at Braunschweig. His talk will be on the miniaturization in photonics, which will then follow up with the talk of Martin Strassburg, who is Director of Global Public Funding and the FG Deputy Chair for the IPCEI ME at ams-OSRAM, with a talk on the digital light, intelligent LED, the technology for the world of tomorrow. And then we will finish today's webinar with the talk from Olivier Kellener, Project Manager at X-FAB France, on the project Photonics Fab, about enabling photonics product innovation with a path to high volume manufacturing. For those who just joined in, please make sure to ask your questions in the Q&A, and then we will treat them at the very end of the webinar. So we won't be asking the questions directly after each talk. The 3 talks will follow each other up. And now I'm very pleased to give the floor to Andreas Waag. It's all yours.
Yeah, thank you, Mireille. I hope you can see my screen now in full scale. Great. It's a great pleasure to be part of this IPCEI seminar. Good morning, everybody. It's about bridging photonics and microelectronics. And in these first 15 minutes, I will talk about miniaturization in photonics and basically what makes photonics different in comparison to microelectronics. So this is the agenda. First of all, a very short intro in who we are, the Nitride Technology Center, NTC at TU Braunschweig, which I'm representing here. Why is photonics different from microelectronics? And I would like to introduce then 2 application scenarios, which are also part of our research at TU Braunschweig. One is photonics for ion trap quantum computers, and the other one is photonics for optical neuromorphic computing. So this is our program for the next 15 minutes. And first of all, very briefly, who we are. We are the Nitride Technology Center at TU Braunschweig. Nitride stands for the gallium nitride family of semiconductors and related technologies. We are having labs for epitaxy, for front-end and back-end processing. So we are able to process 200 millimeter wafers and go through from materials from epitaxy to chips, including hybrid integration with silicon CMOS. I will show some examples later on. We are a big group of more than 20 separate groups from TU Braunschweig and collaborative research centers like the Physikalisch-Technische Bundesanstalt PDB at Braunschweig and also the University of Hanover. And we see ourselves as a research foundry for gallium nitride technology. So why is photonics different from microelectronics? If we talk about photonics, we need key elements to play with photons. And these are light engines, either for the emission of incoherent light or coherent light, LEDs and laser diodes. Then we need devices for light manipulation, and these are, for example, optical lenses or waveguides, but as well nonlinear materials for frequency doubling and electro-optical modulation. And then we need devices for light detection. That's probably the easiest part. We need photodiodes, CMOS image sensors, and so on, and all that contributes to photonic technology. If we look into this from a more fundamental and physics point of view, this is all about light-matter interaction. For light emission, we need material with a direct band gap where this transition between the conduction band and the valence band is an allowed transition for recombination, for efficient recombination. So this is why silicon does not work for photonics. Then for light manipulation, we need a large band gap with a high optical transmission. For waveguides, for example, we are looking into linear and nonlinear interaction of light with matter. And for light detection, we again need another material with a smaller band gap so that these photons which have been emitted here can be absorbed by these detectors. So we create carriers via absorption, and all these light emission, light manipulation, light detection, this is what we need for photonics. Well, which materials come into play here? And this is very different from microelectronics, where we mostly talk about silicon only, let's say. For light engines, for light manipulation and light detection, there is a whole universe of different materials. Light engines, mostly 3-5 semiconductors. This is gallium, aluminum, indium with nitrogen, phosphorus, arsenic, and we are mostly talking about gallium nitride here for the blue and UV spectral range. Then for light manipulation, materials have to be transparent, so it's more about dielectrics, like silicon dioxide, silicon nitride, aluminum oxide, and non-linear crystals like BBO, KDP, ADP, I don't read these lengthy names here, lithium niobate, aluminum nitride, diamond. And for light detection, there silicon comes into play in CMOS detectors, but also 35426 semiconductors. So this is the world of materials for photonics, and you see that it's totally different to microelectronics because it's so diverse, and so many different materials and partially incompatible materials, which we have to bring together to establish a photonic integration. And this is the issue here. If you want to put everything and all these single devices on a single chip, all optical components on one chip, then this is a photonic integrated circuit where we have light couplers, polarization splitters, waveguides, and so on, photodetectors, light emitters. And usually light or laser light is fed in externally, so we need couplers, incoming couplers, input couplers, output couplers, and all that has to be put on a basis, on a chip basis for a compatible technology. So that's really the challenge, and we certainly will hear much more about that later in the third talk today. For such devices concerning dimensions, they are on the order of wavelength quarter, usually in the cross-section to lead to an efficient waveguide. So we are talking about dimensions depending on wavelength on the order of 100 to 300 nanometers. So that's not so small in comparison to microelectronics. However, the flatness of these structures plays a much more critical role than in microelectronics. And the reason for that is that we are dealing here with electromagnetic waves, which have a portion of the electromagnetic wave which is running outside of the waveguide, so they are penetrating into the environment, and therefore they feel much stronger the surfaces and also the environment of these waveguides. The reason for that is that basically the physical reason that the de Broglie wavelength of the electron is much, much smaller than the wavelength of photons, and therefore we can confine electrons in a much more efficient way in comparison to photons. To confine photons, we need waveguides. A key element for confining photons, we need materials where we have difference in index of refraction. We know that very well from optical fibers, from lasers, for example. You need these changes these gradings of index of refraction also for grading couplers, for input and output grading couplers, when you want to feed light into a photonic integrated circuit. And this is one of the issues. If you stick to material which is compatible, which is more or less lattice matched, then the difference in index of refraction is relatively small, and therefore the confinement is relatively small in comparison to electron confinement in microelectronic circuits, and therefore there is always this spread out wave function which is spreading out and running also partially outside of the waveguide. This is the evanescent part of this mode, and this is what has to be taken care of. And therefore, there is a search for compatible materials, for a compatible material platform with larger differences in index of refraction. And just to show one example is porous gallium nitride. So what you can do is you grow a gallium nitride stack where you can porosify parts of this gallium nitride later on. So the whole stack is fully lattice matched, but due to these hole pores, filled with air, you have a very small index of refraction, close to 1 basically, and therefore you can introduce into a lattice-matched structure a very large index of refraction. So this is one of these attempts to establish a compatible material basis for gallium nitride particularly. And this is one result from our labs, a distributed Bragg reflector, for example, for vertical cavity surface emitting lasers, fully lattice matched to the lattice constant of gallium nitride. Well, these photonic integrated circuits and bridging photonics with microelectronics is a enabling technology for very different applications like datacom, efficient HPC, communication technology, quantum computing, environmental sensing, optical neuromorphic computing, but also augmented reality, virtual reality, and we will hear about that later on in the talk of Martin Strassburg, I'm sure. I will focus a little bit in this second half on the quantum computing applications and optical neuromorphic computing applications. This is my favorite. This is one of the strategic research goals we have at the moment here at the NTC in Braunschweig, using micro-LED arrays for optical neuromorphic computing. But let's first look into ion trap quantum computers and why photonic integration is so important for them. An ion trap quantum chip looks like that. Basically, it's a chip, like a microelectronic chip, but it's controlling ions, single ions, which are hovering at a certain distance, usually around 100 micrometers above the chip surface, and they are fixed by an electric field. And you have to talk to them and manipulate them by laser radiation. And this laser radiation has to fulfill particular specifications, so very small line width, very precise, very constant. And this is how it looks like today. So to feed this chip with the lasers, the labs today look like that. So the chip itself, it may be a square centimeter or so, but the laser environment around it fills the whole room. And this is one of the key targets of the startups and also the research labs working in this area, miniaturizing and scaling the photonics around this ion trap quantum chip. And the laser beams we need for that is to manipulate certain ions like calcium, strontium, ytterbium, and so on. And you see the wavelengths which are needed. They are in the blue to UV range. And this is exactly the spectral range which is made for gallium nitride. So if you want to offer photonic integrated circuits for this wavelength range and for these ion trap quantum applications, then we need to look into gallium nitride-based laser technology, and this is something we are going to do. By the way, the line widths have to be extremely small to be used in these quantum experiments, so it's not enough just to fabricate a laser, but it has to be coupled with, for example, ring oscillators to really pick one particular wavelength with a very small line width, and again, which this can be realized by photonic integration. So the second scenario I want to look into is optical neuromorphic computing. And optical neuromorphic computing basically tries to mimic an artificial neuron or mimic a neuron, to build an artificial neuron. And an artificial neuron has the following function. So there is an input vector, which is the input information. It can be an image of something, or it can be an audio signal or whatever. So an input vector is coming in. Then there is a weight matrix, a summation. This is a multiply accumulate operation. Then an activation function. Every neuron, also human brain neurons, have activation functions, and then this activation is sent over to the next neuron, but not only to one of these neurons, but to many, many. So a typical characteristic of a neuromorphic system is that we have a massively parallel interconnectivity. So each neuron, in the best case, each neuron of the first layer is connected to all the neurons of the second layer, and they are connected to all the neurons of the first layer, of the third layer, and so on. So this massively parallel interconnectivity, it's impossible to realize this with millions of neurons connected to each other in a planar silicon architecture. Therefore, photonic approaches are so interesting. And for that, we are using micro-LED arrays. So basically, each micro-LED is one neuron. And this is a comparison of these dimensions. This is a square millimeter high-power chip, which is on the market, which is usually used for illumination, for lighting technology, a high-power 1 square millimeter chip. And this little part of it is shown here. It's made out of pixels, and you need to control each single pixel separately, up to very large numbers, let's say 1 million neurons controlled separately. And this can only be done by connecting it to a CMOS chip. And this is basically where we need this bridging from photonics to microelectronics. So we connect a silicon CMOS chip with all the driving electronics to a micro LED chip. And this is cross section. This is the whole chip. It's about 1.5 times 1.5 centimeters. It's 250,000 pixels, what you see here. And you zoom in. If you zoom in, you see the separate pixels. So photonic and microelectronic integration is needed here to run these 1 million, or in this case, 250,000 neurons, and separately switching all of them and controlling all of them. And this is also a game changer for gallium nitride technology, because this combination with silicon CMOS driving electronics opens up many, many applications, including optical neuromorphic computing. And we certainly will hear much more about that in the subsequent talk. So this is our chip, which is basically transmitting information, optical information, into our system. And everything is interconnected, because this is the nice property of an LED, of a micro LED. If a micro LED is emitting light, it can easily transfer information to millions of detectors on the other side. So you do not have to put down copper lines to each of the detectors. Light is basically giving you this interconnectivity for free. And this is the advantage which we are exploiting here. Our system at the moment looks pretty bulky. So this is the system. At that time, we were using an EVIOS chip from OSRAM with 1,000 neurons. And it was exactly setting up such an optical neuromorphic system. And this neuromorphic system with 1,000 neurons could already detect handwritten digits. And we see the functionality of the system here in this simulation. What you see here is somebody is drawing a handwritten digit. And the system, maybe I should stop in between. The system shows these 1,000 micro LEDs. Well, not all of them are shown here. These are the micro LEDs. They transmit information to an output matrix. And this output matrix are characters from 0 to 9. And this system identifies these numbers, as you can see here, while the input information is transmitted through this optical neuromorphic system. And here it identifies that this was a 3. What you see here is really fascinating, because this is not really a computer. We do not compute anything like a human brain. A human brain doesn't compute anything, but it perceives basically the input information. So the input information is directly transmitted through the system, and the output information is immediately available in real time, without any connectivity to a HPC center or whatever. And this is the main advantage. And this is also why these optical neuromorphic systems can be so massively energy efficient, much more energy efficient than today's NVIDIA processors. Because, well, I don't want to dive into detail, but finally it turns out that every multiply accumulate operation, every MAC, can be realized by much less than 1 photon. Only a portion of a photon, let's say 1% of a photon, is required to realize a multiply accumulate operation inside this system. That sounds a bit weird at the beginning, but can be proven and is published also. And this brings us to the fact that our systems, the optical neuromorphic systems, which can be realized by micro LEDs, can be a factor 100, 1,000, or maybe even 10,000 more efficient in terms of energy and power consumption in comparison to today's microelectronics.
Thank you so much, Andreas.
Yeah.
What would you then say would be the main take-home messages for today?
Exactly. Thank you. And the take-home message is that gallium nitride technology is a key to bridging photonics and microelectronics in combination with silicon CMOS. Thank you for your attention.
Thank you so much. I would now like to give the floor to Martin Strassburg for the follow-up of this talk and to better understand how we can link photonics and microelectronics. The floor is yours, Martin.
Thank you, Mirel, for the introduction. And my presentation today is about the digital light, and that is intelligent LED technology for the world of tomorrow. And first, let me briefly introduce our company, ams-OSRAM. We have a global presence. We have, especially in Europe, many R&D and production sites, but also have R&D and production sites in Southeast Asia, as well as in North America. And that brings us with our products to be in the sensor market, in the LED market, especially in automotive, but by OSRAM also in the traditional automotive lamp market in a leading position. Not being too much on our company, I just would like to, just give a brief overview of what we are doing. We have an well-positioned place in the component production. So our components are there to power advanced solutions for light and sensor applications. The components, these are emitters such as LEDs, micro LEDs, lamps, or coherent light, so emitting laser, edge emitting laser, and vertical cavity surface emitting lasers. Another part of our portfolio are the sensors, light sensors, biosensors, and image sensors. The emitters and the sensors often need optical micromodules and components, and that is a third part of our portfolio. And last but not least, we are able in our company to fabricate integrated circuits and the algorithms, therefore. So we have here especially emitter, the driver circuits for emitters, sensor interfaces, and sensor processors, including their algorithms. And with this portfolio, we are going into applications for visualization, illumination, and sensing. Talking about a trend what has been seen in the last decade, and what Andreas mentioned in his talk, is the miniaturization of components. And that brought a lot of new opportunities to the photonics. And also it was benefiting it was very beneficial to have the heterointegration between optoelectronics and electronics. On the left side, you have the mini LEDs. So we have the shrinkage of the dimension of the chip to a dimension of 50 to 150 micrometers. And that was typically in applications like full array local dimming backlights and public information displays and TVs. So we really take the advantage of having a maturity of these components of the chips. They have a very good efficiency. And what it allows is that this smaller components now show a significant improvement of the performance of so-called legacy technology, legacy applications. Still, there remains a challenge just according to the dimension of these components. That is a pixel pitch. The picture below is just an example of a rear tail light of a car, giving a good impression that this LED types, you can even have a 3D imagination for such a rear light. And going even farther in the shrinkage, you can go to micro LEDs. These micro LEDs have a dimension up to 50 micrometers, but more important, if you go to the smaller limit, then you are typically around 1 micrometer or even below 1 micrometer. Typically, applications are here, the AR, VR imagers, mobile applications, or consumer direct view displays, like for instance in smartwatches. And the advantages that comes with this is really all the OLED advantages, you know, maybe from the recent generation of direct view displays. So to say it's a contrast, it's a flexibility, transparency. And on top of that, now it comes a high brightness, it comes reliability of the LED technology, it comes the possibility of sensor integration, the better steering of the viewing angles, and the form factor. Still, we have the challenge of the efficiency that comes with the dimension. Here we have really the problem that with having such small dimensions, we come into the lengths where the diffusion lengths of carriers play a role. In semiconductors, the diffusion lengths are between 1 micrometer and up to 20 micrometers. And now you can really see where the problem occurs. When we have a dimension of the chip of less than 10 micrometers, each carrier can easily come to the surface. And as a physicist, I can say the biggest defect of the crystal or the semiconductor wafer is the surface. And that is where this would have a non-radiant recombination. The non-radiative recombination yields then exactly in something like a loss, and we would lose the efficiency. Nevertheless, let me now go a little more into the detail how we fabricate such a pixelated micro LED. What you can see here in blue, that is an epi layer. It is made of gallium nitride with an indium gallium nitride emitting zone. And you can imagine here that the growth direction has been from top to the bottom, and the growth substrate is already removed. And we have a slight pixelation, as you can see here, of the surface of for the pixelated LED. Now we want to get them in close proximity to a driver circuit and connect each pixel of the LED with a pixel of the driver circuit to have an individually addressable LED pixel. That takes something like a structured interconnect layer. Here you can see just here as this metal bumps shown. It is of course much more complicated than a metal bump, this interconnect layer, but this has to be designed in a way that there's no overlap to neighboring pixels. For 40 micrometers, it's still a challenge. If you go even to smaller dimensions, it becomes more advanced. And if we bring it closer and have the bonding of both of the chip and the optoelectronic chip and the electronic wafer, then you end up with a structure, a layered structure, what has an addressable pixel of each individual LED. And when you now want to lit a pixel in a white light, it still takes some next steps, and that is the deposition of a converter material, of a phosphor material, what converts the blue light into white light. We use therefore thin phosphor layers of nanograin phosphor to reduce the losses and to increase the absorption, that we can really have a very thin layer that does not impact too much the aspect ratio of each pixel. And when you then operate such a pixel, you can have individually steered addressed pixels of the LED and have micro LEDs, but can shown in a certain pattern here, and you can use them for several applications. And here you see, after having always a schematic, now how the device would look in real life. Here is the yellow colored phosphor surface. You have a package and you have a surrounded package with an electrical connection, better to be seen in a split view. Here in the split view, you see the surface, you see each individual pixel on the surface. It's more than 25,000 pixels. You have the driver circuit, what has been bonded by the interconnect layer to the LED layer. And then you have a package what has a quite complex setup to allow first to reduce the optical losses, to increase the output, and also to improve the direction of emitting light. And in the end, you have the electrical contacts and the power contacts. So what we are doing that for? That gives now the chance to go in a completely new way for instance, for automotive headlights. If you have such a white light, what is very bright, you can have a dynamically controlled light distribution on the road, and also to not glare traffic on the other side of the road. Here it is as an example what is also possible to give a certain signage on the road. You have here the arrows to show where you have to drive. You can have even lanes. You can also have some other symbols to be projected on the surface of the road. And it would also hold when you increase further the pixel numbers that you can have it for interaction with non-autonomous road users, so-called human beings, for instance. But that's not the only way, but you can apply it for. Here in this video, a first introduction is given to other applications of this technology. You can use it for augmented reality, and very similar as it is used for head-up displays, you would have such a view. Here you see just a split view on an augmented reality glass, and the important part here is where is the optical part, where is the projector? And that would be in the corner of the glass here. It needs to be very small, it needs to be very energy efficient, and the light would be then coupled into the glasses to be overlaid with a real world image and to have a high efficiency and to feature also a high quality of the pictures. The RGB projection is considered. And therefore we would use a micro projector. You see here again the micropixelated LED. Now 25,000 pixels are not sufficient anymore. Here we talk rather about 1 million pixels and have smaller pixels. And to get the RGB, everything is put on a board. We have the red, green, and blue LED. This goes with projection and lenses, the emission of their arrays into an optical combiner, and this combiner is then coupled into the glasses. And the application of such micro projectors can be also different. It's not only AR glasses, it's also, you can consider transparent displays, giving you a 3D impression. You can have it here as an example in a retail area to highlight certain things, or if you want to compare things, you can just get it like that. The other option would be to integrate these LED arrays with sensor functions. These sensor functions then allow really an interaction between the user and the thing what has been displayed on the surface. And running a little bit, because my time is running out, the optical data communication is a very interesting part. As Andreas already said, it is the technology of choice when you want to have a data center operated on a very energy efficient mode. And then you have seen this area of LEDs. You can have here a highly parallel transfer of data. The small dimensions of the micro LEDs and the close proximity of the CMOS drivers allow also high switching rates. And so you can consider like having a 2D QR code, and that can be then transferred through bundles of light guides, and you can have the data communication in those centers, especially in between the boards of the boards in the data racks. Another application would be neuromorphic networks, and here I just skipped to say something about it because Andreas introduced it already, and this would be beyond application, but also a very high potential for future applications. And that brings me to my takeaway messages on our digital light. It benefits from the integration of a microscopic LED pixel on a driver circuitry. You have the light what gets digitally controlled and what is highly energy efficient. The first applications are for adaptive automotive headlights, but we have also more applications coming soon. And it has been developed as a new technology base for novel applications. So it's a new platform what can really revolutionize the human-machine interface. So being almost in time, thank you for your attention, and be happy to take your questions at the end of the session.
Thank you very much, Martin. Indeed, I think there will be many questions. Both your talks show that there's a lot of applications possible and a good link between photonics and microelectronics, which leads me to you, Olivier Kellener, to close the webinar with another view on the bridging between photonics and microelectronics. The floor is yours.
So I'm Olivier Kellener from X-FAB. So I will introduce you with a project that we are starting for photonics, which consists in introducing, enabling supply chain, complete supply chain for the photonics application within Europe. So let's switch to a short outline of this presentation first. We'll start with a short X-FAB introduction, so the technology that we are developing within X-FAB. And then we will go to the details of this project descriptions. We'll go through the technologies that we are enabling in this within this project framework. And then we'll see which market and what are the next steps of the project that we envision at this moment. So first, let's start with the introduction of X-FAB. So X-FAB is a large semiconductor company, pure play foundry. We have 6 manufacturing sites from Germany, France, Malaysia, USA. All of them are automotive certified, and our headquarters is in Belgium. So let's go to the details of our technology offering first. So within X-FAB, we offer many different technologies as a pure play foundry for our customers. So they are organized within 4 different frameworks at this time. So the one is the first one is the CMOS type of applications. So with a little bit more than CMOS, because we are specialized in analog mixed signals, high voltage, NVM, RF, opto, SOI, high temperature systems, and MEMS, all combined on wafers from 6-inch to 8-inch. So our technology nodes are ranging from 1 micron to 110 nanometer. We have a strong expertise as well in microsystem and MEMS that we developed from Erfurt sites and IPCEI. And we are pioneering also technologies like a wide bandgap or power technologies like SiC technologies in our sites in Dresden and in Texas, Lubbock. And for this illustration and this specific presentation, so we'll talk a little more within the 4th direction, which we enable emerging photonics technology. And we are setting up now the first element for getting into this photonics market. We have a little bit of expertise because we started so from 5 years of the development of custom photonic platforms. And we have a partnership already defined with Legentech for high volume manufacturing as well. And I will switch to the details of this emerging photonics market to show and illustrate what is our strategy and what we want to enable more than what we achieved currently. So just let's switch to, let's say, basic definitions. I will not spend too much time because our previous presentation went very much into the details. So just to illustrate photonics, photonics is the science of the light propagation, basically. So the photons are generated for source like lasers, transitioning into some light path into a sink, so a detector, an imager, and this is the science and technology of the light. The photonics integrated circuits, you will hear us talk about PIC circuits. This is an optical equivalent of an electronic IC, basically. Silicon photonics, so is yes the PIC which use the silicon combined with other active circuits. And the most important topics that we want to introduce is the more than photonics, which consists in integrating all the functions, all the elements onto a single chip in order to produce something more comprehensive and with active and passive functions all around on the same chip design. And this is a little bit where our project is landing in order to introduce complete turnkey solution for our customers. So they produce an ID, they produce a design, they use our technology, our design environment, and they have at the end a fully combined application and a chip which is assembled, tested, and so on and so forth. So how to enable this feature? So we briefly get to the conclusions. Our fabs have a lot of synergy. Our teams are striving for innovations. They already produce microfluidic components in our MEMS fab. They already produce microtransfer printing for photonics chiplets and other. They already produce some bricks for photonics, heterogeneous integrations, and already defined platform. But the missing links is really synergy and a more condensed project with other partners that we will define and within the project that we implemented. So what is what we call Photonics Fab? Photonics Fab is a project developed from the initiative of industrial partners. And this is developed to enable the photonics product innovation in the market with a path for high volume manufacturing. This is an initiative from industrial that has been first, let's say, co-opted with IPCEI, and then converted into cooptation with the European and especially ChipGU under the grant agreement which is mentioned in this slide. So we'll switch to the key facts, project scope, and objective of this project. We'll get some more in-depth with respect to the industrial value chain that we are generating, more details about the technology that we are enabling, the application and market of this project, and the availability of this project. So first, this is a consortium with a lot of partners involved, so 12 partners from 9 different countries. The project itself is 47.6 million, and it has started in May 2023 for a duration of 3.5 years. So the goal, what we want to achieve, is to establish a supply chain, a value chain, so including the capabilities of all our partners, combining them and producing, let's say, an offering which is very comprehensive and accessible to any customers, so from small SME to big users, to develop the photonics market application. So what we are planning to do is to extend the technology that we already fabricated, so which are technology initiated from Lagentech on SIN photonics platform, which is also to develop PIC design in SOI from the IMEC platform transferred within X-FAB, which is as well to enhance this technology with heterogeneous integration, so transferring active device onto this technology in order to make a really compact design and complete solution for our partners. So for that, we will use the microtransfer printing ready indium phosphide platform that has been first developed by Smart Photonics, and combine it with our PIC design from SOI, X-FAB and IMEC based, and SIN platform, which is Lagentech compliance. And the goal will be to enhance this technology to do hybrid photonics and package a fully assembled solution by FIX and provide this design environment, PDK, EDA solutions coming from Lucida technology. And finally, demonstrate, because this is important that our customers are confident with our platform to see that the silicon is working, fully operating from our development. And we are, as part of the project, considering 5 different application partners to share and to demonstrate the full capability of our technologies on 2 different markets. You will see it later. So first, the industrial value chain that we want to operate. So around the organization of the PDK and design solutions provided by Lucida. So we will make different flavors, different technology of PIC designs, including SOI technology from X-FAB and IMEC, and Legentech technology, very low loss technology in silicon nitride. We'll get the support of very key research and development institute, European Institute, which are CEA-Leti and IMEC. We will do heterogeneous integration of active component made by Smart Photonics that they will convert the technology to make it compliant for heterogeneous integration. We'll use the packaging technologies from FIX, and we'll demonstrate the global approach, the global supply chain with 5 different application partners, well-known partners: Nokia, NVIDIA, Aribal Technology, Photon First Technology, and Thales Technology. So we will demonstrate the capability of this technology within different application markets. For Nokia, it's more telecom, it's more like a transceiver type of application. For NVIDIA, it's more like datacom and data center application. For Aribal, this is very interesting technology because it's a sensing biochemical approach. It's an olfaction sensor. Actually, it's an electrical nose. And the fiber for Photon First, it's going to be a fiber interrogator based on the silicon nitride PIC design. And for Thales, it's going to be as well a fiber interrogator, but it is based on the SOI PIC design. In terms of the technology, let's switch to the technologies that we want to implement. So the first technology is the silicon nitride low loss. So this is very interesting technology. This is to especially focused to sensing because of this quality of low loss, no signal, very nice noise to signal to noise applications, and especially well suited for quantum computing as well. We have this technology that's going to be prepared with the SOI technology. So this is a co-development with IMEC and X-FAB. Actually, we license the technology from IMEC and we enhance this technology to make it compliant for heterogeneous integration like this. We will do in our fabs, MEMS fabs, microtransfer printing on the solution of Smart Photonics. The solution of Smart Photonics is already available in the market, but it's not yet compliant for heterogeneous integration. So inside this development, they make it compliant, so coupon, printable ready coupon, in order to print those active devices in our components and make them available for our customers. We do microtransfer printing approach, so with combination and support from IMEC, X-FAB, and Smart Photonics as well. So this is a very key technology. So we need to develop. This technology is very complex technology, especially in terms of the placement of the active coupon on the wafer. So we need to optimize the placement and make sure that they land at the right position in our PIC designs. We enhance the technology from fixed with more standardization and co-development of fully compliant assembly design kit. So actually we use the EDA environment. We developed the EDA environment, the design environment from Lucida, in order to make it standardized and compliant to the solution we offer for the overall technology, so that our customer can do some more modeling to the system and make sure that that the packaging is including every details of our technology.
So Olivier, there's many technologies actually available and developing. Could you tell us more about the applications and the markets and the availability of your solution?
Yeah, sure. So just to go more into this section, so just finish with the photonics EDA environment that we are designing with Lucida. So this is really an extensive solution that will include, on top of the general PDK that we offer for PIC design, so PDK as well for heterogeneous integration and assembly activities. And really, in terms of the application and the market that we are targeting, so we are targeting a very wide market at this moment: datacom, AI and computing, telecom, quantum computing technology, as I already mentioned, medical diagnosis and biosensing, which is also a very nice aspect of the photonics technology market, to make some kind of lab on a chip type of application for our partners, automotive and LiDAR application, especially that our technology is well suited for, and advanced reality, virtual reality, industrial and environmental sensor, as we develop with our partners as well. So in terms of availability of this technology, so basically, so our technology is available for early technology access right now. We are starting commercial MPW programs for SIN through Legentech at this moment. Commercial MPW program for SOI is planned for mid of next year, and early access technology for indium phosphide chiplet ready, printable ready chiplets will be available next year through Smart Photonics, and access to the overall platform again next year as well. The packaging and testing solution is already available by today, and prototyping and small-scale production of this, let's say, supply chain is already available through, let's say, our partners like IME and Legentech as of today. So just if you want to have some more details, you can also click on our website. So we have a special website which is detailing more with respect to Photonics Fab as well. If you have any questions, so I think the questions will be able to be answered.
Thank you very much, Olivier, and once again, thanks to both other speakers as well, Andreas and Martin. We have indeed some questions. I've seen, Andreas, that you already answered it in the Q&A, but for those who didn't manage to read the Q&A, I will just repeat the question here so you can also answer it in a bit more detail. So the question was, is the ion trap with the GA the only way or method and material for quantum computing application?
Yeah, thanks for the question. Ion trap quantum computing works with ions, and for that you often need blue and UV wavelengths. So, and they come from gallium nitride lasers usually, or should come in the future from integrated gallium nitride photonic integrated circuits. But there are other wavelengths needed also, some of them in the infrared, and then some more conventional gallium arsenide technology can get in, of course. Yeah, but mostly gallium nitride. Yeah, I suppose that with gallium you mean gallium nitride, no? Gallium nitride technology. Yeah.
I imagine as well. Thank you so much, Andreas. And then also a question for you, Martin. Do you actually use converter materials for the RGB micro-LEDs?
Yeah, RGB can be done with direct conversion, but direct conversion is very delicate because you need a strong absorption, and it also reduces a little bit the efficiency. What we in the moment use is direct emission from semiconductors. For the green and blue, we have gallium nitride material. And we have also very efficient indium gallium arsenide phosphide material for red emission. And that is in the moment the best solution, unless we have efficiency increase in direct conversion for green. And the efficiency increase also has to come with not a widening of the full width of maximum of the emission curve of the converter, because that would reduce the color gamut, and then the brilliance of the pictures, what you can see and display, are not so good anymore.
That's true. Thank you so much for this additional information. And then Olivier, for you also a question. What challenges do you see in the packaging, and where is the packaging actually done?
So the packaging is challenging for sure, because as of today, the packaging solutions, they are custom made. Each customer is designing almost his own packaging. And in terms of the photonics fab application, we would like to make it more, let's say, standardized. And this is the objective of our ADK, actually, that we are designing. Most of the packaging, all the packaging activities, they are conducted by our partner, which is FIX. This is a well-known packaging partner within the European community, as for sure. And yeah, this is where we are, where they are at this moment. We usually made a custom design packaging, custom made packaging, but our objective within our project is to make, let's say, more standardized solution, so silicon proven solutions, to minimize the number of design iteration from our customers, and make sure that they can have a functional device at the end of our supply chain.
Very clear, thank you. And then one last question, because we are running out of time, but I think it's a very interesting one in the Q&A, where Ignacio also thanks everyone for your interesting presentation, which I fully agree on. And the question is, may SiC be considered as suitable for light manipulation application like modulators or similar?
Silicon carbide, yeah. Yes, indeed, silicon carbide is also an interesting material. It has a larger band gap. So if the wavelength is not too short, it's also a suitable material. Absolutely.
Perfect. Thank you.
And there is,
sorry, Andreas, to interrupt you.
No.
Also here, it is then the question how good you can synthesize this material, because of defects and traps inside this material can create some absorption, some scattering, and some losses. And here, silicon carbide is a quite major material, but then depending on which type of it you want to use, it has advantages and disadvantages.
Very clear. Okay, with that, I would really like to close today's webinar. So once again, thanks to all three of you. I think we've seen many new ideas on how to combine photonics and microelectronics. And as the IPCEI MECT is really about collaborations and setting up new projects, I hope that during the next General Assembly, you will get many interactions with those who were present at this webinar. And of course, everyone else who is listening to us, stay tuned for the next topics coming up in the next year. And looking forward to meeting you all on the General Assembly in The Hague in the Netherlands, end of November. Thanks again to our three speakers, and thank you for watching, and we will see you soon. Have a good day.